Hey, everyone. As Devin mentioned, my name is Frank, and I'm the engineering manager of the Web UI platform team, and we're part of the React group at Facebook. This is actually my first time attending ReactConf. Thanks. This is actually my first time attending ReactConf, so I'm nervous to be standing up here, but thanks. But so excited to tell you more about how we're building the new version of our website and a few things we learned along the way. So this is what the new website looks like. But first, let's take a look at how we got here. Facebook began as a simple website made with PHP. I know, it looks really old, right? All right, here we go. Facebook began as a simple website made with PHP, and over the years, we built richer and more interactive features like messaging and live videos. But our pages started to look less like this little island of PHP, and more like an iceberg of JavaScript and CSS. Engineers wanted to build with React and Relay, but each time they tried, it only added to the iceberg, making the website heavier and slower. It was extremely difficult to build the product experiences that we wanted with the technology stack that we had. There were too many different ways of doing things, and moving fast for so many years had accumulated debt that was now slowing us down. We wanted to deliver a better user experience, which to us meant implementing a design system with a modern design language and support for theming. As Yuzi mentioned, we care deeply about accessibility, and we wanted to build a component library that embedded best-in-class support for this out of the box. We wanted to speed up the site, but performance is not just about page loads. A truly app-like experience on the web also delivers seamless interactions whenever you click, tap, swipe, or scroll. And all of these things were technically possible with the old stack, but they required so much work to deploy and maintain across all the different ways of building UI that we never got around to it. We knew that a redesign alone wouldn't be enough. We had to rethink how our website was put together and rebuild it from the ground up. So we constructed our new website as a single-page app. React organized our HTML and CSS into HTML and JavaScript into components from the top down, and with GraphQL and Relay, we co-located our queries declaratively in our components. The only thing that we hadn't reorganized into components was CSS. But we didn't want to do it just because we could. CSS is already declarative and built into the browser, and for many of us, the ease of tweaking styles is one of the most fun parts of building for web. Many websites, including my own, use idiomatic CSS, and it works great. So the idea was not to discard it or reinvent the wheel. It was to explore whether we could make it easier to maintain when we have hundreds of engineers working together on the same code base while retaining all the good parts of CSS that we love. Since Christopher Chateau presented this idea in 2014, many great open source libraries have been developed to embed styles and components. And they're each awesome in different ways. We had some very specific constraints for our new website, so we decided to create our own library that synthesizes ideas from many different frameworks, including introducing a few of our own. While the library is not yet ready to be open source due to dependencies on our internal static resource infrastructure, and even the name is still experimental, I'd still like to share some concepts from it with you today. But don't worry, we're not asking you to adopt anything. Our library has been working well for us, but if you don't share requirements or use cases, something different might work better for you. Our #1 priority was to make it easier for styles to be read, understood, and safely changed when it's unfamiliar code. Or let's be real, even if it's your own. So let's take a look at some code. Here we have some simple CSS. And let's add some HTML. What color will this text be? It'd be reasonable to expect blue. After all, blue comes later in the list of classes where we use them. But CSS rule precedence actually depends on the order of classes in the style sheet. So you'll be seeing red. Or at least the text will be red. Anyways, this is already confusing with just one style sheet and one usage. If these classes were split across 2 files, The color applied would depend entirely on how they were bundled and the order in which they were inserted into the page. We tried to make this more straightforward. Using our library, we now author styles using a familiar syntax that is inspired by React Native and other frameworks. And we guarantee that the styles applied follow the order of arguments at each call site. You never have to scroll up or switch files to check your style sheet. In fact, if we switch the order of arguments here, the text would become red. We can now sort our style rules alphabetically or however you like. I'll come back to this later to explain how we made this work, but you can already see that we're still using CSS style sheets and class names under the hood, and this one change helped many engineers have confidence in their code when collaborating to build new features quickly. Another capability we needed to support was theming. And one of the first things our designers asked for was dark mode. We used to write a lot of code that looked like this. We'd put a class on the body or some ancestor and override styles. Or like this. We'd try a redesign, and once it shipped, new engineers had no idea which blocks were safe to remove, so inevitably, this would happen. It's all fun and games until the specificity wars. By adopting CSS variables, we eliminated some of these anti-patterns and made the cost of a theme proportional to the size of the color palette instead of the size or complexity of the component library. You may have noticed that CSS variables propagate their values to their subtrees in the same way that React context does. This means that for themes that only remap CSS property values like colors or spacing, we don't need the full power of React context, and we can delegate all this restyling work to the browser. CSS variables can also be used to theme certain types of icons, especially ones that are monochrome. Instead of passing SVG files to image tags, we inline SVGs into the HTML using React. We did this by taking each icon's SVG file and generating a React component from it, which enabled us to style the icon according to its props and the current theme. Under the hood, this works using CSS variables just like HTML. Because these SVGs now are effectively JavaScript, they can be bundled and delivered together with their surrounding components for a clean one-pass render. No more flickering of icons that pop in afterwards. And these icons can change colors smoothly at runtime without requiring an additional download. In case you missed that, here it is again. Focus on the menu icons. All right, shout out to our designers for making this so pretty. Build steps mean that what we write does not need to match what we send to the browser, and we can take advantage of this for accessibility. Here's one example. Many browsers today have a font size setting that defaults to 16 pixels. And when you change it as a user, it effectively alters the browser's built-in style sheet to apply a different font size to the root element. To respect this setting, we needed to avoid overriding this rule. And we needed to change all our font rules to use rems, which are a unit relative to the root element's font size. However, designs are usually made in CSS pixels, and the conversion rate is a tricky 16 pixels to 1 rem, so we were never going to get the math consistently right by hand. But we can make the library do this conversion for us. We code in pixels, and the browser receives values in rems. Now when you change your font size setting in the browser, the text updates automatically. All right, this one's really subtle, so look closely at a specific line of text. You can pick anyone, but keep staring at it. Ooh. This gives people the option to change only the font size or only their text size without accidentally triggering a tablet or mobile layout like full-page zoom might. Because the styles we write are now embedded inside JavaScript files, we can also use JavaScript tooling like type checkers and linters. This helps us catch and fix typos, detect unused styles and eliminate dead code, or even suggest switching to a component to avoid cross-browser pitfalls. But not everything is statically analyzable, so sometimes we need to rely on runtime checks. In our development environment, if elements are inaccessible, incompatible with dark mode, or are extremely slow to render or fetch data, we can visually and functionally block them out. By providing a highly visible contextual error with actionable recommendations, we can help engineers quickly solve the problem. So far, I've only shown styles local to a file, but sometimes we need to be able to pass styles around. For this, we have composition. Here's a quick example, but I won't have time to go into too much detail in this talk. We have a base component here that accepts a style object that it can merge into its own styles. And we have another component that passes some of these styles into the base component. The style object can be strongly typed and only accept specific properties, such as margin, or even specific values, such as 0 or 4. This adds flexibility to how components can interface with other components in a structured way. All right, let's jump back to that first example and dive a little deeper. I've made red the default and added a font size rule to help illustrate how our library works. From the style rules at the top, our library generates atomic CSS. This means that each class refers to a unique property value pair. The library then transforms the values in the component to refer to these generated classes. If a component uses style composition and has external styles to merge, this is where our library stops because we need to retain the CSS property names to handle dynamic collisions. But since this component only has local styles, it can optimize further using static analysis. It turns the class name value into simple Boolean and ternary operators for each generated class in order to handle property name collisions. And this eliminates the function call. Now there's no more need for the styles block at the top, so that's eliminated as well. All we have left is the optimized component and the generated atomic CSS in a separate file. We've eliminated almost all the runtime costs of CSS and JS and retained compatibility with server-side rendering. When we take all the generated atomic CSS from across our site and combine it into one style sheet, we can achieve more savings. To illustrate this, with the old way we wrote styles, we would accumulate lots of duplicate rules, like these ones, within and across files. Our new library merges these rules under one class name. And browser engines are optimized to match elements that have this type of simple class selector. Thanks to this deduplication, the size of the generated style sheet grows much slower than the number of styles or features that you write, because it's proportional to the number of unique declarations. On the old site, I measured a total CSS size of over 400 kilobytes. And that's just for the homepage load after gzip compression before you start interacting with the page or visiting other pages. With all these changes to how we author styles and generate CSS, the new site requires only 74 kilobytes of CSS total shared across all the newly built pages and interactions, and that includes the dark mode implementation. And now I'd like to welcome Ashley to talk about how we restructured our data and JavaScript.